In today's experiment, you'll learn how to generate and identify some well-known non-metallic elements and compounds. The compounds you'll be generating include of carbon, sulfur, and nitrogen. In particular, generating carbon dioxide, sulfur dioxide, a mixture of nitric oxide and nitrogen dioxide. All of these are colorless gases except for nitrogen dioxide, which is a brown gas. In addition, you will be generating hydrides of sulfur and nitrogen. Hydrogen sulfide is a foul-smelling toxic gas. One of the nicest descriptions is that it smells like rotten eggs. You'll probably recognize the odor of ammonia because it's very frequently used in home cleaning. Finally, you will also generate several elements. In particular, you'll be generating oxygen, which is recognizable by its support of combustion, of course, support of life. And also you will be generating two of the halogens, in particular bromine and iodine. Well, let's look first at the oxides. The most common of the oxides is carbon dioxide. You see it or its effect every time you open up a can of soda or some other bubbly drink. There you go. Any baking or leavened goods such as bread or cake owes its fluffiness to the generation of carbon dioxide during the baking process, either using baking powder, which contains sodium bicarbonate, or else from yeast. Alka-Seltzer, its famous fizz, is due to the fact that you're generating carbon dioxide in the Alka-Seltzer process. And finally, there is solid carbon dioxide. That's called dry ice. It's about minus 60 degrees, used for keeping ice cream cold. It's very cold. But it's also used for producing mists on the television screens. The oxides you're studying today are also important with regard to environmental effects. In particular, the greenhouse effect, acid rain and pollution, and destruction of the ozone layer. The increase in concentration of carbon dioxide in the atmosphere is the major contributor to the greenhouse effect. Right or wrong, this effect predicts the gradual warming of the Earth's surface with melting of some of the polar ice and flooding of what is now ocean shoreline. This gradual increase in carbon dioxide concentration in the atmosphere is due to the burning of fossil fuels, such as coal, oil, and gas for energy. Let's look at the cause of the greenhouse effect. The sun's radiation, when it hits the Earth's surface, is transformed into infrared or heat radiation. This is then re-radiated out into space because nitrogen and oxygen are transparent to infrared radiation. However, carbon dioxide absorbs infrared radiation and then re-radiates it back as heat. Now, some of this heat is directed at the Earth and will warm the surface. Therefore, an increasing concentration of carbon dioxide, particularly in the lower atmosphere, will cause an increased warming in the Earth's surface. Two major pollutants of the atmosphere and the principal causes of acid rain are sulfur dioxide and the nitrogen oxides, in particular the nitric oxide and nitrogen dioxide. These are both acidic gases. The major source of sulfur dioxide pollution is the burning of sulfur-containing coal in Midwestern power plants. It's also formed in the production of metals such as copper and lead from their ores. The nitrogen oxides are produced in small amounts by combustion of fuel and air. And although it's produced only in small amounts, there's a lot of combustion going on, and so this adds up significantly. For example, nitrogen oxides are produced in a car's engine, and your car is inspected for its nitrogen oxide emissions. The chemistry of acid rain and pollution is this. Both sulfur dioxide and these nitrogen oxides react with water in the atmosphere or in your lungs to form acids. Now, sulfur dioxide will eventually form sulfuric acid, which is a very strong acid, and the nitrogen oxides will form nitric acid. Now, when formed in the atmosphere, these fall to the earth, particularly during rain, and increase the acidity of some lakes and streams. But these acids, whether in lakes or streams or in your lungs, tend to kill off living matter, both animal and vegetable. Finally, we'll take a look at what effect nitric oxide has on the ozone layer. Ozone is a molecule made of 3 oxygen atoms. It is a very toxic form of oxygen, and at the Earth's surface, it is a very serious pollutant, even in small amounts. Los Angeles has its periodic ozone alerts. However, in the upper atmosphere, where you don't have to breathe it, ozone forms a layer which provides the useful function of blocking much of the ultraviolet radiation from the sun. These are the powerful cancer-producing rays. Now, high-flying jets such as the Concorde are releasing nitric oxide into the air, and this is reacting with the ozone. This decrease in upper atmosphere ozone concentration may eventually allow ultraviolet radiation levels to become dangerously high at the Earth's surface. We should also note that chlorofluorocarbons, these are the things which are used in refrigerators, air conditioners, and aerosol spray cans, will also react with ozone and are of concern to the environmentalists, but we'll not be studying them today. Well, with this background, I think we can look at the experiment that you'll be doing. Well, let's see what it takes to generate these oxides. We'll be using sodium carbonate to generate the carbon dioxide. I'll put some of that sodium carbonate in that tube. And we'll be using sodium sulfite to generate the sulfur dioxide. There. And finally, we'll be using potassium nitrite to generate the nitrogen oxide. That is the combination of nitric oxide and nitrogen dioxide. Once we have those salts in there, we will acidify them to generate the gases with sulfuric acid. I just put that in. Watch carefully for any effervescence or anything. You see a lot of bubbling took place there. There's not too much bubbling there. Seems to be a little bit happening there, but not too much. Well, you will identify these by their characteristic effervescence, their odors, and also the color of the gases. You may have to heat this. As a matter of fact, it's always a good idea to heat these up to make sure that you're getting complete reaction. Let's heat these and see how they change. All right, here it is after heating, and you can see a rather dramatic change. We don't have smell-o-vision, so you can't really see all the changes which have taken place, but at least this will show you some of the characteristics of these gases. The reactions just presented can be written in the following form. These are net ionic reactions and include only the ions actually involved in the reaction. The ions such as potassium and sodium are left out. Let's turn now to the generation and identification of oxygen gas. We will catalytically decompose hydrogen peroxide. Now, hydrogen peroxide is found in many medicine cabinets at home. It's used in coloring and setting of hair and also in cleaning cuts and scrapes. Today, we'll be using manganese dioxide to catalyze the oxygen formation. Actually, the same reaction takes place when you put hydrogen peroxide on a cut or scrape, except that instead of manganese dioxide, oxidase, which is an enzyme in your tissue, is used to decompose the hydrogen peroxide to oxygen and give the cleansing action. All right, here we have a flask in which we have generated oxygen. We have another flask which has just air in it. And here we have a flask in which we have generated carbon dioxide. Let's see what happens when we put a glowing splint in there. We have a glowing splint here, and you can see that the splint bursts into flame. It stays a glowing splint if you put it in air, but if you put it in carbon dioxide, it goes out. So here's some differences that you can see between oxygen, air, and carbon dioxide using a glowing splint. Does this property of carbon dioxide suggest a possible use? And you will generate two other elements, bromine and iodine. These are halogens. Perhaps the best known of the halogens is chlorine, which is a yellow gas. It's used to kill bacteria in water and to make bleach. Seen here are bromine, which is this orange liquid, which forms an orange gas, and iodine, which is a black, sort of purple-black solid, which forms a purple vapor. You will also generate and characterize the hydrides hydrogen sulfide and ammonia. We'll look at the formation of ammonia first. You'll be taking ammonium chloride, allowing it to react with sodium hydroxide, and this will generate the water-soluble basic gas ammonia. You will identify this either by its smell, or a more sensitive reaction is to use moistened red litmus paper. In the presence of ammonia, moistened red litmus paper turns blue. Now, ammonia is basic, that's the opposite of being an acid, and red litmus paper turns blue in the presence of a base. We'll carry out the reaction in front of the household ammonia bottle. We'll mix the ammonium chloride, put that in here, and the sodium hydroxide. Notice I'm using a 4-inch test tube, one of the small ones, because if you're generating gas, the 4-inch test tube will fill faster. All right, now we're ready for the test, and we could use either just smelling for ammonia, or more sensitive, we would use the litmus test. If we don't get a positive test with this, what we will do is we'll heat it and then try these tests again. All right, here's the test for ammonia. Now what we do is we have moistened a little piece of Pinklets paper and we put it inside the test tube so it doesn't touch the side. And you can see that it is evenly turning blue. Where it does touch the side, since there is sodium hydroxide in it, it will turn blue anyhow. But the fact that the middle, which is not in contact with any possible sodium hydroxide, is turning blue, means that you have a vapor there, which is basic, which probably means that you have ammonia. Finally, you will identify an unknown. The unknown will be a solution of one of these. In identifying it, you will generate one of these, except for thioacetamide, which will generate both hydrogen sulfide and ammonia. Do not confuse what unknown is for what it generates. On the other hand, remember, what it generates will tell you what it is. To identify your unknown, take a 1 milliliter portion and add about a milliliter of HCl to it. Then look for effervescence, odor generation, or some vapor colors. This should do both before and after heating. Now, if you do notice something, you've probably generated one of these gases. If you haven't noticed, then you probably have not generated one of those. But in any case, go on to the next step. Add the manganese dioxide and heat. Again, what you're looking for is effervescence or a change in color of the solution or the gas. If you do notice something, you probably generated one of the elements here, oxygen, bromine, or iodine. In any case, at this point, check for the possible generation of ammonia by your unknown. It's a very simple test. What you do is just take another 1 milliliter portion of your unknown and add a milliliter of NaOH to it, and you heat. Now you can check for ammonia simply by its odor, but better yet, confirm it with the litmus test. That is, pink litmus paper should turn blue in the presence of ammonia. Well, when you're through with this sequence, you should probably have identified the possible generation of 1 or 2 of these species. So at this point, you should confirm that what you have identified is correct. Now, to run a confirmation test, for example, if you think you have generated SO2, take a little of your unknown, about a milliliter, and add to it sulfuric acid. And again, heat or whatever, and check again for the odor. And this time, because sulfuric acid is a non-volatile acid, you can use the litmus test. That is, test the vapor with a little bit of moist blue litmus paper, and of course if it turns pink, that would indicate that the gas it generated is acidic. Or for example, if you think you have generated oxygen, definitely make sure you use the going splint test because, for example, carbon dioxide, he's still bubbling out, and it will of course give you a totally opposite test with the glowing splint test. Well, let's see how this is done. All right, let's start the analysis of our unknown. We'll take our unknown, about 1 milliliter of it, and we'll add to it about 1 milliliter of HCl. Watch for effervescence here. There's nothing much happening. Shake it up. No smell, no color. Let's heat it up here. Now, it's turning a little bit yellow, but other than that, there isn't much happening. All right, next step then, apparently there's nothing much in the line of CO2, SO2, or the nitric oxide or H2S. We put the manganese dioxide in here. Oh wow, it's really turned dark orange at this point. And let's just heat that up a little bit. Oh, there's a purple vapor there. Oh, we pretty well know what it is at this point. But nevertheless, let's continue the analysis so that we know we haven't made a mistake. Take another milliliter of this and add to it some sodium hydroxide. Shake it up again. Can't smell anything here. Let's heat it up to make sure. And as long as it's heated up at this point, we'll take a little bit of litmus paper, the pink litmus here, see whether or not any basic vapors come off. just barely moisten that paper then. And because it's hot in there, we'll put this in and see if, well, nothing much is happening except at the sides where the sodium hydroxide is turning the paper, so that it doesn't appear that any ammonia was generated. Finally, we'll just do the confirmation test. It appears that it's one of the halogens which was generated here. And to do the confirmation test for halogen, we'll just add hexane. And before I add the hexane, I'll turn off the flame so I don't have a fire there. And add the hexane. Take it up. Oh, I got a pretty purple color there. Let's take a look at that in close-up. All right, here's a close-up of the confirmation test. This is diluted it slightly, so color shows up a little bit better, but this is the purple color in the hexane. You see the hexane layer on top. And I'm also showing the purple vapor we got when we heated this tube. And finally, what I'd like to show is this piece of pink litmus. You see, it's all around the edges where it's touched the sodium hydroxide on the side of the test tube, but the rest of it remained pink, which means that no ammonia vapors were generated, which is the test for ammonia. So that's a negative. This is a negative test. Well, I think at this point you have a very good idea of how to do this. And so I'll just let you start.